A very good evening to all of you. I'm Ramesh Jayaraman, the Chief Scientific Officer from TheraIndx Life Sciences based out of Bangalore in India. The title of my talk is Pharmacokinetics, Pharmacodynamics based optimization of experimental design in drug discovery. The outline of my presentation is as shown in this slide. I'll explain briefly about pharmacokinetics and pharmacodynamics, and the importance of proof of concept in the drug discovery process. I'll talk a bit on the experimental design needed to evaluate the proof of concept in early stages of drug discovery. I'll illustrate this approach using a case study, and finally I will summarize. And I'll take some questions at the end from which I received from the participants early. Pharmacokinetics and pharmacodynamics are two integral components of the discipline of pharmacology. Pharmacokinetics is the study of concentration over time in an organism. The organism could be a microorganism all the way up to human beings. One could also say that it is the study of time course of drug concentration in the body, simply what the body does to the drug. Pharmacodynamics studies the effect of a compound or a drug based on its concentration. In other words, it could also be called as what the drug does to the body. If you integrate pharmacokinetics and pharmacodynamics, we get the PK/PD, effect over time. PK is essentially the link of the observed response. And this forms the basis for setting the dose, regimen, and duration to treat a disorder or disease in the clinic. I will keep referring to these terms through my presentation. So what is proof of concept in drug discovery process? As you're all aware, the drug discovery process is divided into two major components. One is the preclinical stage and one is the clinical stage. All drug discovery programs begin with a target identification that is implicated in a disease. And then hundreds of thousands of compounds are screened on this target, in which yield potentially promising compounds, which we call as hits. And then some of them are moved further up, which show drug-like properties, which is referred to as the lead compounds. And from the leads, specific candidates are then chosen for optimization, eventually to yield a preclinical candidate, which enters the preclinical development program where safety and toxicology studies are done, eventually giving rise to the candidate drug, which is then progressed to clinical trials. I'll talk a bit on the target now. The target is essentially a pharmacological target associated with disease or disorder. It could be in the humans or animals. For example, a receptor or an enzyme. The hypothesis that the project wants to confirm early on in the drug discovery process is modulation of the pharmacological target, either by inhibition or activation in vivo, results in a therapeutic effect in animal models and human patients. For example, inhibition of a kinase which has gone aberrant inhibits cancer cell proliferation. The proof of concept is nothing but the confirmation of this hypothesis in a preclinical animal model of disease. How does one establish proof of concept in drug discovery? Let's take a look at the stage where the hits move into leads. By this time, a lot of compounds are profiled in vitro for efficacy and potency on the pharmacological target in terms of Emax and EC50. They're also tested in cell functional assays where the hypothesis of inhibiting the target inside a cell results in a specific physiological endpoint. Some of these compounds are also profiled in vitro for ADMET, that is absorption, distribution, metabolism, excretion, and toxicology, ranging from physicochemical properties, solubility, permeability, plasma protein binding, metabolic stability studies, and cytotoxicity. Promising compounds from this enter evaluation of pharmacokinetics in animals, the preclinical species that is, estimating a variety of important PK parameters. At this stage, a lot of structure activity relationships happen between in vitro ADMET and in vivo pharmacokinetics, as well between in vitro target potency and PK. But one point which is often not investigated is the relationship or the structure activity relationship between the molecule of interest and its pharmacodynamic activity. So what I'm trying to say in the slide is the combination of in vitro potency, drug-like properties, and optimal pharmacokinetics, do they result in the therapeutic effect in the disease model? This is what we call as proof of concept. Now, why is this important? Lack of demonstration of proof of concept for leads at this stage is a certain no-go for project because we are not able to confirm the hypothesis with which the project began. And it is a major decision point for the project. Before one goes to understanding the proof of concept, I would like to point out some major factors that determine the outcome of proof of concept studies. The fundamental differences are shown here. One of the most important parameters or differences one could put it is the compound concentration in vitro assays. They remain constant. For example, an enzyme or a receptor is profiled at constant concentrations. Whereas in vivo, let's say the disease model, the concentration of the compound varies continuously over time, which is nothing but the pharmacokinetics. The second important difference is there are barriers between pharmacological target and the compound in vivo, whereas in an in vitro assay, essentially there is no barrier. For example, when an enzyme is being assayed in the presence of a compound, it is only the compound and the enzyme. There are no physical barriers between these two. Third point is that the concentration of the pharmacological target itself could be different. It remains essentially constant in an in vitro assay, for example, enzyme assays, and they could vary in vivo. The pharmacological target turns over, that is synthesis and breakdown. So prediction of efficacy or the design of critical efficacy studies based on in vitro potency and PK alone can be misleading. The other major set of factors that determine the efficacy of a compound in animal disease models is the disease model itself. The first important point one has to consider is the location of the pharmacological target. Is it extracellular or intracellular? For example, most enzymes reside in the cytoplasm of the cell, whereas most receptors are in the cell plasma membrane, the body. Now, if you look at infectious agents like bacteria, viruses, parasites, and fungi, they could be residing in the blood or in the tissues or inside the bones. Take, for example, cancer cells and tissues. They could be deep inside the tissues, they could metastasize, and they could also enter the brain. Another important factor is the pharmacokinetics itself, as described by absorption, distribution, metabolism, and excretion. The four processes are determining the free concentration available to act on the pharmacological target. These processes also determine the time taken for the compound to reach the target site, if the target is inside the tissue. Formation of metabolites is another important component which could affect the efficacy. Like I said in the previous slide, the turnover of the target inside the body, like for example, synthesis and breakdown, could affect the time taken to see the effect. For example, if the target is part of a metabolic pathway, inhibiting the target when it's upstream and the effect to be manifested takes some time as the effect is at the end of the pathway. So keeping all these factors in mind, it becomes very critical to establish proof of concept for the lead compound before the optimization program begins. To be able to demonstrate proof of concept, experimental design is very important. The hypothesis at this stage is, let's say, blood, plasma, or tissue concentrations, read as pK here, of the compound in animals exceed the in vitro active concentrations, and therefore efficacy should be achieved in the animal model of disease. However, what is the experimental design for testing efficacy? What should the dose levels be? What should the dose frequency be? What is the duration of treatment to get efficacy? These answers are not readily available from in vitro potency and PK data alone. So in order to establish proof of concept, it's very important to perform single dose pharmacodynamic effect time course studies. And three major parameters determine the effect. The first thing is the onset of the pharmacological effect. It's the time taken to observe the effect post-dose. And the intensity of the pharmacological effect is the magnitude of the effect post-dose. And the duration of the pharmacological effect is the excuse me, duration of effect post-dose. By performing such a study, important information can be gleaned. For example, there could be differences between excuse me, concentration and effect. The delayed effect could manifest in terms of a lag between peak compound concentrations in plasma and the effect observed. It also could manifest in terms of differences in pharmacokinetic half-life and the pharmacodynamic half-life, which could be due to the turnover of the target. What I mean by this statement is there is a possibility that the compound's concentration half-life could be short, whereas the effect could last for a long time. Much of the compound concentrations are below limit of quantitation. And then there is the lack of correlation between concentration and effect. If metabolites are formed, one would see that the concentration of the parent compound is much lower than therapeutic concentrations, but yet we observe effect. It's quite possible that the metabolites are also active on the target. The second is the compound is not reaching the target site. If the target is inside the tissues, if the compound does not reach the tissue, you may not see the effect. Or is it insufficient concentrations at the target site? So the onset, intensity, and duration of pharmacological effect, referred to as OID, forms the basis for setting dose frequency, and the duration of dosing for key pivotal efficacy studies. I'll illustrate this approach using a case study where a lead compound, let's refer to it as X, from an anti-infective program. The project goal is to develop an orally active excuse me, antibacterial agent to treat bacterial infections in skin structure and bacteremia. So these are the in vitro properties of compound X. It's very potent on the pharmacological target, 10 nanomolar. It's very potent in inhibiting one of the pathogens, that's E. coli. Its MIC, or the minimum inhibitory concentration, is 0.031 micrograms per ml. The compound kills the bacteria in vitro in a concentration-dependent manner. So in vitro, compound X is very potent. How about the oral pharmacokinetics? Remember, I told you that the compound is being developed for an oral indication. This graph here shows the plasma concentration of the compound, excuse me, over time at dose levels 5, 10, 30, 100, and 300 milligrams per kg. Shown here in the horizontal dotted line is the MIC of the compound. So one can visually assess how the compound concentrations are relative to the MIC. And this table here lists the pharmacokinetic properties in terms of Cmax, that's the peak concentrations achieved in the plasma of the compound, the area under the plasma concentration time curve, as well as the T above MIC. How does one interpret this data? If you look at the ratio of the peak concentrations relative to the MIC, you can see that it exceeds the MIC from 12-fold to almost 700-fold. And the AUC by MIC, this is an important parameter in anti-infective pharmacology, also ranges from 18 to 1000. And if you look at the graphs here, the time for which the concentrations exceed MIC range from 2.5 hours to almost 24 hours at the highest dose. The inference from this data is that PK appears to be sufficient to achieve antibacterial effect. But what is the onset time, the magnitude, and duration of effect following single oral doses? This is not intuitive from this data. Before going to the single dose pharmacological time course experiments, we have to understand the animal model of disease. In infectious diseases, bacterial infectious disease, that is, the neutropenic mouse thigh infection model is a standard model for characterization of anti-infective pharmacology. The key features of this model are bacteria are generally injected into the thighs of the mice, where they multiply in the interstitial fluid. This model mimics tissue infections, that's the acute bacterial skin and skin structure infections. PK measurements are routinely done in plasma, serum, or blood. And it has been shown that plasma PK measures correlate well with effect in tissues in animals and humans for a wide range of antibiotic classes. In other words, this model is well validated. So for the project to test lead compound X, the biopsy mouse was chosen. It was made neutropenic because one likes to study the effect of the compound alone minus the immune system's effect. The pathogen, of course, is E. coli here, and it's infected in the thigh. Around 10 to the power 6 colony-forming units are injected in the animal. And the doses studied were 5, 10, 30, 100, and 300 milligrams. It's administered orally, and the treatment is initiated at 2 hours post-infection. The duration of treatment is 24 hours. I'll come back to this in a minute in the later slides. The main readout in this model is the bacterial numbers in terms of log CFU per thigh. So the single dose PD effect time course was done with this compound to demonstrate proof of concept. This graph shows the bacterial numbers over time for different groups. This red line is the infection control. And these lines, green, purple, blue, and black, show the time course of bacterial kill and regrowth following single oral doses of lead compound X. The arrow here shows the time of dose, and this line shows the limit of quantitation of bacteria. How does one interpret this graph? The first thing that is obvious is that the effect, or rather killing effect of lead compound X begins very rapidly. That is, onset is 15 to 30 minutes post-dose. The magnitude of killing, you can see here, increased with dose, that is in a dose-dependent manner. The bacterial numbers are reduced almost up to LOQ here at the highest dose. The duration of effect increase with dose. Here, the effect is you see a peak effect and then bacteria begin to regrow, but at different rates. At the highest dose, there is a flat phase before, after which the bacteria begin to grow. However, none of these reach the levels what you see in the infection. If you consider the onset, magnitude, and intensity together, it is apparent that single doses are not adequate to eradicate bacteria completely. The data suggests that the compound has to be dosed at least 2 to 3 times in a day for sustaining this effect. Some important information from single-dose PD effect time studies are one compares the PD with the PK. The first observation is and time at which the peak effect was observed were the same. In other words, there was no time lag between the concentration peak and the effect peak. The plasma concentrations correlated with effect in tissue. Since the effect was immediate, it suggests that the compound rapidly equilibrated with concentrations in the interstitial fluid where the bacteria reside, and therefore the plasma can be a surrogate measure for this compound, and this could have important implications all the way up to clinic, where one can suggest that plasma concentrations can be used as surrogate measures. The maximum effect observed at 15 to 30 minutes post-dose, it's clear that the regrowth rate is dependent on the time for which the concentrations exceed the MIC here. As the time above MIC increases, the time to regrow is also longer. The duration of the specific experiment, it could be fixed at 4 hours because we see a maximum effect at 4 hours. However, we need to extend it simply because there is regrowth observed. If the bacteria were wiped out and did not regrow, then the duration of the experiment would be just 4 hours. Now, in projects, in general, in anti-infective projects, 24 hours is chosen as an endpoint. Now, if you compare the effect at 24 hours and at 2 hours, you would miss out if you did not sample the points between 2 and 24 hours. You would miss out on the peak effect of the compound. And if one reads out at 24 hours, it seems that the compound did not show much efficacy, except at the higher doses. They seem to be at the same levels at when the infection began. So the efficacy of the compound could be underestimated if one does endpoint experiments without studying the time course experiments. That brings us to another important point. What are the intrinsic pharmacodynamic properties of the compound? The key questions are, what is the maximum efficacy? Here's Imax for the lead compound in 24 hours. What is its in vivo potency in terms of IC50? Up to now, we have seen that it's potent in vitro, but what is its potency in vivo? Third, when coupled to its MIC using for maximum efficacy, Imax. How should the design look? If you recollect the single dose time course, PD time course that is, bacteria begin to regrow. So to get a full dose response curve, we have to administer at least 7 to 8 dose levels. In this case, 5 to 300 milligram per kg because it showed linear PK, given once, twice, thrice, or 4 times in 24 hours. Evaluate plots of effect in the thigh versus each of these parameters, which are important determinants of efficacy for anti-infectives. Fit an appropriate pharmacodynamic model and establish the Imax IC50 in vivo. These are the intrinsic PD parameters for the lead compound. This slide shows the intrinsic pharmacodynamic properties of the compound. This graph shows a plot of the bacterial numbers at 24 hours plotted against plasma AUC by MIC. The reason plasma AUC by MIC is plotted against the bacterial counts here is that we observed there was not much of a correlation between peak concentrations and the time above MIC. So if you look at the behavior of the graph, it's a classic sigmoidal dose response curve, starting with no effect in the absence of the compound. That's the baseline effect, close to 9 logs at 24 hours. At the highest AUC by MIC, the effect appears to taper, or in other words, reach saturation. So the net effect of the compound in this system is the Imax. That works out to 6 logs. That means the bacterial counts are reduced by almost 6 logs by this compound in 24 hours. And its in vivo potency, that is 50% of Imax, is close to 30. One has to remember that at the highest dose levels, for example, these points here, each point represents a mouse. The 300 milligram per kg given twice, that's Q12 hours, is not very different from 300 milligrams per kg given every 6 hours. That is to say that excuse me, this dose is not very different from this. So the conclusion from this experiment is excuse me, that an AUC by MIC of 2000 is required to achieve maximum antibacterial effect for the lead compound X. If you remember the questions asked in the previous slide or a few slides ago, what dose, what frequency, and what duration for the lead compound for this project? The dose is 300 milligrams per kg given every 12 hours for a period of 24 hours to achieve the maximum effect. So if one consolidates all the data towards establishing proof of concept, we saw that in vitro it killed very rapidly, shows linear PK, and then there is a rapid kill and regrowth in single dose PD effect, and then we have characterized the intrinsic PD properties. The most important observations from this experiment is that PK and MIC, or the killing rate in vitro, showed correlation with the in vivo antibacterial effect. In other words, the proof of concept has been essentially established for this compound. The second important point is the plasma concentration correlated with effect at the site of infection, which is the thigh here. The onset, intensity, and duration was dose proportional in vivo. Another important point is that the in vivo effect time course is clearly different from the in vitro. Remember the point I made on concentrations being constant in vitro assays and variable in vivo assays. So one has to keep this in mind when you design efficacy experiments. And the single dose PD effect, that is the onset, intensity, and duration, helped us to set the dose, regimen, and duration for the lead compound. So the learning for the project from doing such a study is that this lead compound has an intrinsic efficacy. It's an intrinsic property of the lead compound to demonstrate 6 log reduction in 24 hours, which corresponds to an AUC by MIC of 2000. Since all the members of the same chemical class act on the same pharmacological target inside the bacteria, they will all have the same intrinsic efficacy, but their potency could be very different. The second important point is The IMAX IC50, what we have demonstrated here, achieved at an AUC by MIC of 2000 for X. This number, it means a lot for the project. It could serve as the reference for comparison with the standard of care if the project is comparing it with the standard of care. It could be a comparison with other compounds coming from the same chemical class. That is, whether the new members during the optimization program, do they have the same IC50 or do they have a better IC50 or are they poor? This could also serve for comparison with different chemical classes in the lead program. Last but not the least is that this number is the target to be set for the clinic, which has been shown to be translated well into human beings for other classes of antibiotics. Further learnings for the lead optimization program is the goal for the lead optimization program should be to improve in vivo potency, that is IC50 for AUC by MIC, retaining the Imax, that's the efficacy. Another important point that emerges from this is that efficacy of analogs of the lead compound coming from the same chemical series, that is, can be predicted using PK in AUC and MIC alone. This is the direct benefit of performing single dose PK/PD time course experiments. So what parameters should be optimized in the lead optimization program for this chemical series is AUC for the PK point by reducing clearance or increasing bioavailability. The second one is to reduce the MIC, that is the target potency has to be increased. And of course, one has to keep in mind the safety. Now, the POC experiment is very intense, but I believe it's essential before you begin the lead optimization program. Why? Firstly, it establishes PK/PD relationships, that is a concentration and effect relationship. Lack of PK/PD is a cause of concern for the project. Second, it decreases the number of compounds screened in pharmacology studies. There is a significant reduction in resources and time to screen compounds. And this becomes very useful where animal models are long duration. Some could extend from weeks to months. So I would like to summarize this presentation with a few take-home messages. The experimental design is critical for performing pharmacodynamic, in other words, efficacy studies early on in the preclinical drug discovery programs to establish proof of concept. And that's done by performing single dose PD time course studies, which can yield important information on the potential of the lead series, here the lead compounds, to demonstrate proof of concept. The three important parameters one has to, excuse me, characterizes the onset, intensity, and duration. Lack of translation of in vitro potency and PK to in vivo efficacy raises alerts for the project before embarking on resource-intensive lead optimization phase. So that was the presentation I had to make in this webinar, and I've got a few questions from the audience, which I've collated here based on the similarity, and I'll try to answer them here. The first question asked was, if the target is located in tissues, would the tissue concentrations be more relevant than plasma concentrations? This is a very valid question. However, there is a caveat in determining tissue concentrations. In most cases, when tissues are homogenized, the concentration established in this homogeneity is really not a concentration. It's a mixture of the compounds concentrations inside the cell, compound bound to cell membranes, compound found in interstitial fluid, and compound concentrations in blood. So we really don't get a true excuse me, measure of concentration in the tissues. However, one can establish a tissue to plasma partition coefficient and make an assumption that this could be a concentration in tissue, knowing its physicochemical properties. The second question is, how early on in the lead identification program should POC be done? I would say that the sooner you do this, the better. That is, at the stage where you have sufficient data to say that the lead compound is very potent on the target, it has met the PK criteria of the project. This is the stage that the compound has to move into an efficacy study, proof of concept study, to just to make sure that the project is on track and we are not misled. The point that the POC is demonstrated at this stage puts the project at lesser risk and therefore on a firm track, and it becomes much more easier for the medicinal chemist to now optimize the compound. The third question was, in the example shown, excuse me, the endpoint was reduction in bacterial numbers. Can the endpoints also be regrowth, post-treatment, and emergence of resistance? The answers are yes. I only showed the reduction in bacterial numbers to illustrate the concept of proof of concept here. It could be regrowth as well as emergence of resistance, which are equally important pharmacodynamic parameters in an anti-infective program. The fourth question was, the design shown in this presentation does not appear to be feasible in chronic disease models like NASH or CKD, as they can run to months. And compound amounts at this late stage may not be sufficient for detailed characterization. What are your comments? Yes, I agree that it may not look feasible for such chronic models. But what I would like to point out here is, if you have biomarkers that are correlated with disease, it is good to run proof of concept studies using those biomarkers. Second, I would still say run this project POC study with the lead compound so that the project gains valuable information for translation of in vitro effect to in vivo effect. If that translation is not seen, then it's a cause for concern for the project. Last question I would like to answer here is that the question asked was, can we apply this design for topical applications? The answer is yes. The same principles hold good. Here, of course, you're looking at concentrations on the skin, but yet that also undergoes the process of absorption and elimination. And one would like to see that application on the skin correlates with effect. It could be effect on various PD parameters according to the disease area. With that, I would like to end my webinar. I'd like to thank all the members who attended, who registered for this webinar. If you have any other questions or comments, I would be very happy to answer. You can please write to me at the email ramesh.jairaman@TheraIndx.com. Thank you very much.